I'd like to start to get started. Everything at MIT runs late, but we're only about 5 minutes, so I think technically we're right on time. So I'd like to welcome all of you to the annual McGovern Spring Symposium, and this one is on computations from synapses to systems. So I have to first say thank you very, very much to Lori McGovern and the McGovern family for their support of our institute, and in particular for making this symposium possible. And I'd also like to extend a very deep thank you to the headquarters staff at McGovern. They've been incredible in helping me, the most inexperienced faculty member here at MIT, organize this very, very complicated symposium. So everything that goes right today is down to them. Everything that goes wrong today is likely down to me. So I'd also like to say thank you very, very much to our speakers who have traveled a collective 20,000 miles from Canada, the West Coast, the East Coast, the UK, and Europe to be with us here today, and no less on Mother's Day weekend. We really appreciate you coming to share your work with us today, and we're really looking forward to hearing all about your take on computations from synapses to systems. So what I want to do in just a minute or two is to pose two challenges to sort of frame what's going to happen today. The first is something of a definition of terms. This idea or this concept of a computation is a very nebulous one. Something that I've learned in my first year here at MIT is that computations mean very different things to different people. Some of us think about computations at the level of single cells, say orientation tuning in the visual cortex. Many of us think about computations at a much higher level, more cognitive processes like goal-directed decision-making and valuation. And so I'd like for us, for the speakers and for the audience, to think about what counts as a computation. Where do we draw the boundaries around different kinds of computations? What does it mean to have a computation at this level versus another level? And how do we merge those levels or move between those levels? So I'd really like to encourage the audience to push our speakers a little bit on some of these issues. So the other thing I'd like to think about as we hear all of these exciting talks today is an issue about goals. What does success look like as we study neural computations? Tom Insel, former director of the National Institutes of Mental Health and now at Google, just visited us here at MIT not very long ago. I had a chance to meet with him, and after talking with him about what I was doing in my lab and kind of questions I was asking, he asked me, what does success look like for you, Mark? In 5 or 10 years, how will you know that you've answered your problem? And I really wanted to have a great answer for him, and I didn't, and was really disappointed about it. He mentioned that he's asked this question to a lot of people, both in brain science and artificial intelligence, and no one seems to have a particularly great answer other than, well, we'll know it when we see it. That may well be true, but it's not tremendously satisfying. So it's something I'd like us to think about is as we're doing all this work on neural circuits and computation and trying to figure out, what is it about computation in the brain that gives rise to the mind? How can we think about sort of milestones on our way to the thing that we will know when we see? And let's be sure that when it actually shows up, we will know it. So with that, I would like to thank you all again so much for coming. And I'll turn it over to Michael Fee, our first session chair.